Modern commercial aviation operates under a startling truth. Human pilots actively control aircraft for only minutes during typical flights. From shortly after takeoff until final approach, sophisticated autopilot systems manage every aspect of flight operations with precision that exceeds human capabilities. These AI-driven systems process thousands of data points per second, making continuous micro-adjustments that maintain optimal flight paths, fuel efficiency, and safety margins. The technology represents decades of aerospace engineering evolution, combining GPS navigation, weather radar, traffic collision avoidance, and flight management computers into integrated systems that operate with reliability rates exceeding 99.9%. Modern autopilot doesn't simply follow predetermined routes. It actively adapts to changing conditions, optimizes performance parameters, and makes split-second decisions that human pilots couldn't process fast enough. Autopilot systems excel in areas where human limitations become apparent during long flights. Precision navigation. GPS-guided autopilot maintains flight paths accurate to within meters, continuously calculating optimal routes that account for wind patterns, air traffic, and fuel efficiency. Human pilots cannot match this mathematical precision over extended periods. Fatigue resistance. Autopilot systems operate with identical performance throughout 12-hour flights, while human pilots experience cognitive degradation, attention lapses, and decision-making impairment during extended operations. Multi-parameter processing. Modern autopilot simultaneously monitors altitude, airspeed, heading, engine parameters, weather conditions, and traffic while making continuous adjustments. Human pilots must prioritize attention between competing information sources. Weather navigation. Advanced autopilot systems use real-time weather radar data to automatically navigate around turbulence and storm systems, calculating optimal deviation routes that minimize flight delays while maintaining safety margins. The heart of modern autopilot lies in flight management computers, FMC, that represent sophisticated AI systems. Route optimization. FMCs continuously calculate optimal flight paths, considering wind forecasts, air traffic restrictions, fuel consumption, and arrival time requirements. These calculations update hundreds of times per minute, adjusting routes for maximum efficiency. Performance management. Autopilot systems optimize engine power settings, climb rates, and descent profiles to minimize fuel consumption while maintaining schedule requirements. This optimization exceeds human pilots' ability to process complex performance variables simultaneously. Traffic integration. Modern autopilot interfaces with air traffic control systems and other aircraft through automatic dependent surveillance, maintaining safe separation while optimizing traffic flow patterns impossible for human coordination alone. Emergency response. Autopilot systems can execute emergency procedures faster than human reaction times, automatically initiating emergency descents, engine failure procedures, or collision avoidance maneuvers based on sensor inputs. Current autopilot technology incorporates machine learning elements that adapt to specific aircraft characteristics and operating conditions. Adaptive control systems. Modern autopilot learns individual aircraft performance characteristics, adjusting control inputs based on weight, balance, and aerodynamic variations that affect each specific aircraft differently. Predictive analytics. AI systems analyze historical flight data to predict optimal performance parameters, maintenance requirements, and operational efficiency improvements that enhance safety and reduce costs. Weather pattern recognition. Advanced systems use machine learning to recognize weather patterns and turbulence signatures, enabling proactive flight path adjustments that improve passenger comfort and safety. Failure prediction. Emerging autopilot AI can predict potential system failures before they occur, initiating preventive measures or alternative procedures that maintain safe operations. Despite advanced capabilities, autopilot systems require human oversight and intervention for critical decision-making. Strategic decision-making. Human pilots make high-level strategic decisions about route changes, weather avoidance, and emergency responses that require judgment beyond program parameters. System monitoring. Pilots continuously monitor autopilot performance, ready to intervene when conditions exceed programmed capabilities or when manual control becomes necessary. Communication interface. Human pilots manage communication with air traffic control, passengers, and ground operations while Autopilot handles routine flight control tasks. Abnormal situation management. Complex emergency scenarios require human creativity and problem-solving that extends beyond Autopilot programming, particularly for situations not anticipated in system design. Autopilot technology demonstrates remarkable safety performance. Accident reduction. Airlines using advanced autopilot systems show significantly lower accident rates compared to predominantly manual flight operations, particularly in weather-related incidents. Precision approaches. Autoland systems enable safe landings in visibility conditions that would be impossible for human pilots, including zero-visibility fog conditions at equipped airports. Fatigue-related error prevention. Autopilot systems eliminate human fatigue factors that contribute to pilot errors during long-range flights and overnight operations. Consistency performance. Automated systems provide identical performance standards across all flights, eliminating human variability in technique and decision-making quality. Next-generation autopilot technology continues advancing toward full autonomous flight. AI decision-making. Advanced machine learning systems will enable autopilot to handle increasingly complex scenarios currently requiring human intervention. Integrated air traffic management. Future systems will coordinate directly with air traffic control AI, optimizing entire airspace utilization without human air traffic controller involvement. Predictive maintenance integration. Autopilot AI will monitor aircraft systems' health, automatically scheduling maintenance and adjusting flight operations based on component condition predictions. Passenger experience optimization. Future autopilot will optimize flight profiles for passenger comfort, automatically adjusting climb rates, turns, and descent profiles to minimize turbulence and motion sensitivity. Modern aviation represents successful human-AI collaboration where autopilot handles routine precision tasks, while human pilots provide strategic oversight, creative problem-solving, and adaptability for unexpected situations. This partnership leverages the strengths of both artificial and human intelligence, creating safety levels impossible with either technology alone. The result is aviation's safety statistics that make commercial flying the safest form of transportation, with autopilot systems contributing significantly to this achievement through precision, consistency, and reliability that complements human judgment and experience. Every safe flight demonstrates the successful integration of advanced AI technology with human expertise, pointing toward a future where autonomous systems handle increasingly complex operations while human oversight ensures adaptability and safety in unpredictable situations.